次のページもそれはね、よろしいですか。
はい。
大丈夫です。大丈夫です。
大丈夫です。はい。じゃあ15分からなのでしばらくお待ちください。
はい。
Okay, shall we start the second talk? The second talk will be given by Yasusada Nambu from Nagoya University, and he is going to tell us about the entanglement partners of super horizon mode. So please.
Thank you for introduction. And I also give thanks for organizer of the workshop to give me a chance to have a talk in this session. So today I am going to talk about the entanglement in cosmological situation. This is a plan of my talk. In this talk, I discuss on entanglement in cosmological situation, especially entanglement structure of Dojita inflation. First, I will give you a short explanation of background and motivation of these topics. Then, as a tool of analysis of entanglement Dojita space, I will introduce the concept of entanglement harvesting in Dojita space. Then the third part is main part of my talk. That is to construct the partner model in Dojita space. So first, I will briefly review the standard scenario of cosmology, especially for the structure formation. One important purpose in cosmology is to explain origin of structure in our universe. So for this purpose, in modern cosmology, origin of large-scale structure in our universe is explained by based on the concept of inflationary expansion. This figure represents a very rough history of our universe. very early stage of universe, we have rapid exponential accelerated expansion of universe called inflation, which is caused by the some kind of quantum scalar field called inflaton field. After that, Big Bang follows. Then after that, due to the gravitational instability, structure of our structure in our universe is formed. So it is very important to understand the quantum nature of quantum fluctuation in the early universe to understand the origin of structure in our universe. Then, but based on this scenario, structure of our universe comes from the quantum origin. So some conceptual difficulty arises to adapt to this scenario. Anyway, due to the quantum fluctuation of inflaton field, this fluctuation is transferred to the fluctuation of geometry by Einstein equation. So the fluctuation of energy density of quantum scalar field is related to the geometrical fluctuation, curvature fluctuation, or the fluctuation of Newtonian potential. This is the origin of gravitational instability for the structure formation. Anyway, inflation prepared the seed of structure formation in our universe. So to understand this scenario in detail, we must use the quantum theory. The quantum fluctuation of the inflaton field is calculated by using a standard quantum field theory in curved background spacetime. So in this talk, we assume the simple scalar field as a quantum field. So the quantum field is quantized, and in the second quantized form, the Hamiltonian of the scalar field is represented as this form. This is very standard form of the free scalar field. This part is a standard Hamiltonian for the harmonic oscillator. And this part is peculiar to the quantum theory in expanding universe. Form of this operator is so-called squeezing operator. And this coefficient is A is a scale factor of universe. So the scale factor is time dependent. This term appears. So due to this term, squeezing is occurred for the quantum state. In other words, this term causes so-called particle creation in expanding universe. And the standard treatment, particle creation is represented by in terms of so-called Bogoliubov transformations. And if the created number density of particle is represented by using the Bogoliubov coefficient, this is a well-known formula of particle creation. And in this case, resulting quantum state after squeezing is written by this form. This is also very standard form of Gaussian state, so-called two-mode squeeze state. So, inflationary scenario, we know that here the tangent hyperbolic tangent R is coefficient of this squeezing, smooth squeezing state, and R is called the squeezing parameter. So in the standard scenario of inflation, we must require that the value of squeezing parameter is about 100, very large value. Anyway, vacuum state evolved to the two-modal squeezing state by accelerated expansion of the universe. And as a limiting case of the R becomes infinity, it is known that this state approach is so-called EPR state. And here, I show that the behavior of two-point correlation function of inflaton field based on the standard calculation of the curved space-time, quantum field theory in curved space-time. And this plot shows that for small scale, correlation decays like this line, and this behavior is the same as the standard vacuum states for in the Minkowskian space-time. However, for larger scale, over the so-called hyperhorizon scale, some constant, nearly constant value remains. So we think we regard this nearly constant value as a seed of becomes the seed of structure formation in our universe. So cosmic inflation generates large-scale quantum fluctuation beyond hyperhorizon scale of the jitter space. This is definition of scale. So we regard this as the origin of primordial fluctuation. This is a very standard scenario of inflation and origin of primordial fluctuation. But as I have said, there appears some conceptual difficulty to interpret this standard scenario. If we adapt to quantum fluctuation as initial seed for structure formations, some conceptual difficulty appears. That is, usually quantum expectation value is adapted as initial condition for the classical evolution. This is usually obtained for cosmologists to calculate the detail of structure at present. So we call this as assumption of classicality. This assumption matches quantum quantity to the classical initial conditions. Rule is very simple. We replace quantum expectation value as we interpret quantum expectation value as classical statistical average. So in this interpretation, original quantum operator is replaced or interpreted as some C number random Gaussian variables. This is an assumption of classicality. So I will say this statement in a bit different expression. We assume that the condition we assume condition of classicality, and the assumption is that the existence of local probability distribution reproducing quantum correlations. That is, quantum correlation can be represented as local hidden variable theory. This means that the theory guarantees Bell's inequality. So for bipartite system, the condition is equivalent to the state is separable. There is no bipartite entanglement. if this condition is held, we can say that quantum expectation value can be evaluated using some type of classical statistical model. So also we want to prepare classical initial condition for structure formation. Still fluctuation itself is quantum origin, has a quantum origin. So we must check the validity of this assumption of classicality more detail. This is the main motivation of this subject. So for this purpose, we investigate the structure of entanglement in digital space based on concepts of entanglement harvesting. This is a protocol of detecting the entanglement of quantum field. So idea is very simple. We prepare some particle detectors with internal degrees of freedom. For simplicity, here we assume that qubit detector, which has 2 energy level. This particle detector interact with inflaton field or some quantum field. So we can, by using this detector, we can extract the entanglement of quantum field as follows. This is a setup of harvesting. As an initial state of 2 detectors, we assume separable state. Then switch is on and the detectors interact with scalar field for some period. After that, we measure the state of 2 detectors, and from that data, we can judge that the original target, original quantum field has entanglement or not. This is because if we obtain the results that the final state for 2 detector is entangled, as a local operation cannot generate entanglement, this result implies that the original quantum field has entanglement, and the 2 detectors measure the entanglement of quantum field. So this protocol is called entanglement harvesting. We apply this protocol to the digital case. This figure shows the schematic setup of this thought experiment. Initially, we prepare 2 separable qubit detectors. In digital case, 2 qubit detector, a separation of 2 qubit detector grows in time as universe is expanding. So the after some time, separation of these 2 detectors becomes larger than the horizon scale. So judgment of the entanglement is the same as previous slide. So as if we measure the final state of 2 detectors and they are entangled, we conclude that the inflaton field has entanglement. So based on this sort of experiment, we can investigate quantum correlation into jitter space. And this consideration can be useful to theoretical justification of the origin of classical primordial fluctuation and the experimental verification of quantumness of very early primordial fluctuation. So this is a result of calculation. This plot shows the horizontal axis is separation of two detectors, and vertical axis is parameter of qubit detectors. That is combination of switching time and energy gap of two energy level. And this shaded region corresponds to the entanglement harvesting is successful. That is, the two detectors can harvest the entanglement of inflaton field. So, for judgment of entanglement, we use the concept or the measure of negativity. In this two qubit case, negativity is given by this formula. First term is transition amplitude of this type of qubit detector. And the second term corresponds to the so-called local noise. And this term causes the independent local noise for the two qubit detector A and B. Anyway, so this formula shows that if the local noise is too large, negativity can become negative. That means that entanglement vanishes. So the result of this plot can be represented as a very simple plot, this one. So we have some limiting distance of two detectors here. This scale corresponds to just Hubble horizon scale. So the for small separation compared to the Hubble horizon scale, entanglement harvesting is possible. But separation is too large, so larger than the horizon scale. Entanglement harvesting will become impossible. So we can interpret the behavior of harvesting as follows. For large R, local noise destroys quantum correlation and the system becomes separable. This is very direct interpretation of this result of this behavior. And here, local noise means that the so-called thermal fluctuation given by the Gibbons-Hawking temperature in the jitter space. Anyway, so a pair of qubit detectors cannot access entanglement on super horizon scale because typical possible harvesting scale is determined by Hubble horizon scale. So at first glance, this result implies there is no quantum correlation in super horizon scale. So classical quantum to classical transition occurs on super horizon scale. But we must be careful. This is only one aspect. This conclusion is derived based on the only one aspect of entanglement, so-called bipartite entanglement. So we must check multipartite effect of entanglement to confirm this result. For this purpose, we consider the different, a bit extended version of entanglement harvesting.
Can you accept the questions?
Yeah.
There are two questions.
Yeah.
Please.
I just wanted to ask how the detailed information of inflaton is important. For instance, what happens if we consider other vacuum? I guess
other vacuum?
Yeah, I guess.
For example, alpha vacuum and so on.
Yeah, or excited particles. So.
That may cause the bit different behavior with entanglement. So, but I'm not sure the. But it may depend on the type of state, assuming maybe.
But would you think that this, the absence of the super horizon entanglement is kind of robust?
No, I'm not. I do not say that entanglement is absent on super horizon scale, but just by part entanglement cannot accessible on super horizon scale.
Right. I mean the non, for in this prescription, not seeing entanglement is robust for other vacuum, or maybe it's not important. Probably you want to say opposite by considering more detectors.
Sorry, you are saying about the two detectors case?
Yeah, so my question was, so you are saying that as long as you consider only two detectors, this, our max is just around the horizon scale. And just my original question is how robust is it? And if we consider other vacuum or...
Sorry, I cannot answer that question at present. So,
Okay, thank you.
But my feeling, it seems, looks like very robust. So if we change, modify, or adapt to different type of state, I think result will not change.
Okay, thank you.
This is my expectation.
Yeah. So okay, can I ask a question?
Yeah.
Okay. So you're trying to detect this bipartite entanglement through these two detectors. Why can we just compute this entanglement of two regions? I mean, which are separated.
I tell that story in later.
Oh.
So this is just one method to entanglement harvesting. And the another method I will explain the entanglement between two spatial regions.
Okay. Oh, I see. So did you find the entanglement or? Yeah,
I can find. But it may depend on how the two systems are prepared.
Okay, thanks.
So just straightforward the extension of 2-qubit case, we consider the multiple detectors case. The setup is here. We prepare two groups of particle detectors and evaluated the bipartite entanglement between these two groups. This shows the result of entanglement as a function of number of detectors. Vertical line is maximal possible separation that the harvesting is possible. This result shows that as a number of particle detector increases, distance of possible entanglement harvesting is also increases. So increasing the number of detector corresponds to the taking into account the effect of multipartite effect of entanglement. So this result shows that detection of super horizon scale entanglement is possible with multiple detectors, or that is taking into account the multipartite effect of entanglement. So another setup of entanglement harvesting is this. In this setup, we do not use the qubit detector, but more general type of harvesting. Essentially, mechanism is same as case of underweight detectors, but in this case, we extract the local information of quantum field by assuming some kind of coarse graining for the quantum scalar field. Setup is very simple. And this is my setup, and we define the canonical degrees of freedom from the original scalar field, by introducing some window function in momentum space. In this case, we simply assume that the step function like window functions and the Kc correspond to the UV cutoff. So by defining the coarse-grained field, it is possible to check that Q and P obey the standard commutation relation for the continuous variable. So this procedure means that we introduce the standard canonical variable by using the coarse graining of quantum field. This picture is just an image of this operation. For small coarse graining scale, scale of coarse graining is given by hand. So we change the coarse graining scale and investigate how the entanglement structure changes as a function of coarse graining scale. This picture is for the small coarse graining scale, and this picture represents the case for the large coarse graining scale. Well, in the representation of the configuration space window function, this procedure is represented as this picture. We identify for two spatial points, we introduce the localized mode of canonical variable associated to each different point. So adapting this procedure, we can evaluate the entanglement between two localized spatial regions. So entanglement for the continuous variable is also easily can be evaluated using the negativity for continuous variable case. This plot is a result of entanglement harvesting. So basically, structure of entanglement as a function of coarse graining scale, this corresponds to the separation of two regions, is same as qubit detector case. And entanglement harvesting becomes impossible for larger scale comparison than the Hubble horizon scale. So for sufficiently small separation, AB is entangled and entanglement harvesting possible. On the other hand, two regions separate greater than the Hubble horizon scale, AB becomes separable, and the harvesting is impossible. And the critical coarse graining scale is roughly correspond to the Hubble horizon scale. So the model AB become separable for distance larger than the Hubble horizon, and this behavior is the same as qubit detector case. So we summarize the observation done so far. Why the state is separable on large scale compared to Hubble horizon scale? This behavior is independent of, maybe independent of detail of harvesting protocol. From this observation, we pose the question, why is the model AB become separable for super horizon scale? So one explanation is, as I have already said, thermal noise with a given working temperature destroys quantum correlation. As a temperature is proportional to H, Hubble parameter, so this separable scale appears in the harvesting is compatible with the thermal temperature given by Hubble parameter. Or we can explain this behavior from a bit different viewpoint, that is the effect of multipartite entanglement. Maybe both two feature is related. So to understand this behavior, we consider this system from viewpoint of multipartite entanglement and the reformulate the problems as follows. This picture shows that the original setup and A and B mode, we are interested in mode between entanglement between mode A and mode B. But AB are embedded in some environment that means some environment that the complement of A and B. So this setup can be represented as this: A, mode A and mode B and mode E. This tripartite system is tripartite mode constitute to a total system. So by studying the structure of entangled sharing between these three modes, it may be possible to understand why this entanglement occurs at the just Hubble-Huazhen scale. So this setup is just the purification of for preparing the purification for original A mode and B mode. So this environment is corresponding to the partner of original AB mode. So by this setup, adapting this setup, is it possible to understand the emergence of classicality in digital space? This is my question. So for this purpose, we will try to find out the explicit form of the partner for two modes A and B. Okay. So this is the main part of my talk, and this part is ongoing and with the collaboration with Koji, Yamaguchi, and Tohoku University. First, we shortly review concept of purification and entanglement partner. That is basic concept in quantum mechanics. So purification. First, we consider the arbitrary mixed state A. Then it is known that mode A can be purified by adding suitable ancillary mode, and it is possible to make total systems pure. This figure, A is purification partner of A, and the total system A and A bar can be pure state. So the here show the very simple derivation of this statement, but it may be trivial, so I skip. So in this procedure, if the original A mode is pure, then A and A bar becomes product state, and they cannot have a quantum correlation. We know that well-known example of concept of partner that appears in Hawking radiation. So this is very good example of concept of partner. We consider the standard scenario of Hawking radiation that occurs by the gravitational collapse of matter field. This plot shows the space-time diagram, not Penrose diagram, space-time diagram of the situation. This line shows the world line of the collapsing matter, and after some time, event horizon appears and black hole is formed. In this situation, nature of quantum field is completely characterized by using the two-mode Bogoliubov transformation. So in outer state, for the outer state, in-mode vacuum state becomes the two-mode discrete state, that is entangled state, given by this equation. And so this is a superposition of mode U and mode U bar. The mode U represent the outgoing particle mode in outside of event horizon. On the other hand, U bar mode corresponds to the infalling mode inside of black hole, which has a negative energy from the asymptotic far observer. Anyway, this is a prediction of the quantum state by the gravitational collapse. So this, as inside of black hole is not accessible, if we make the reduced state by tracing out U bar mode, we obtain the thermal state with temperature TH at Hawking temperature, which is related to the surface gravity of black hole. So in this situation, partner of Hawking radiation is infalling U bar mode, which form the two-mode squeeze state as a total state. So U bar is a purification of Hawking particle U. So based on this consideration, we can we try to obtain the entanglement pattern for the mode AB that is prepared as a harvesting entanglement in digital space. But different as a station is a bit different. For the Hawking radiation case, two mode Hawking particle and pattern mode are traveling, moving. So, but in cosmological station, mode is like a standing wave, so the picture becomes a bit different. Anyway, purpose of my program, my program is in digital space. We want to identify partner mode for AB, which are defined as two spatially local mode of 2 points. So this picture is a very rough expectation of a situation. We prepare original target mode A and B and construct the purification for this mode by adding 2 modes. The total 4 mode becomes pure. So by making this purification, it may be possible to understand the entanglement behavior between original A and B by considering the sharing structure of these four modes. So here we explain how to construct the partner mode. As already introduced, we define local modes of quantum field using the window function, which determines a spatial profile of modes. So we consider with following definition of coarse-graining operators. Information of the local mode at spatial point xj can be measured by Untitled type detectors. So, for example, if we want to obtain this type of operator at spatial point j, we consider this type of interaction, which mu represent the degrees of freedom of unrooted detector. So by this interaction, we can extract the information about the given spatial point xj. But here, W1 and W2 profile of windows, which determines what type of shape of mode we want to, we are interested. So this is given by hand as the form of or shape of this window function depends on the programs that we want to treat. Anyway, for given set of operator O, it is possible to identify 2K independent modes satisfying the following two conditions. Condition one is mode. We call mode as a pair of canonical variable Q and K. They obey standard commutation relations. And mode constitute a pure state. This is just a condition for purification. And set of modes satisfy these two conditions called QIC, quantum information capsule. This name is appears proposed by Ota-san and Yamaguchi-kun in their paper. So by introducing a concept of QIC, information associated with original mode is completely contained or characterized by obtained QIC. So it is very useful to discuss the structure of information between modes. We applied this concept to our program, and the detail of procedure is written in their papers. So now I show the detail of construction and result. As a demonstration, we first consider the purification of local mode A in digital space. This is a single mode case. So, but we prepare the single mode using the coarse-grained field as before, and we assign canonical operator at the spatial point x1. This is defined by this integral with momentum space window function. They obey their standard canonical commutation relation. Then we consider the following linear map for operators. This map is very simple. Annihilation operator A is mapped to the minus IA, and A dagger is mapped to IA dagger. Then applying this map, original canonical variable is mapped to this type of this form of operators, which are independent of original Q and P. So we introduced a two-mode system characterized by the following these four operators. And this map F preserves the commutation relation and covariance. So we call it the original mode as target mode, GUZI. Then we prepare the GUZI and FGUZI by applying the previous map. And the commutation relation is like this. And the covariance between original mode and mapped modes has this equality. This is a feature of this map F. So we assume here that the covariance of original target modes in the standard form, so-called standard mode. That means that covariance of momentum and Q is same. So with these preparations, by redefining the combination of these four operators, it is possible to identify independent two modes. That means by suitably recombining the combination of operator, we can obtain the combination of operator that shows the following property. GUZI A is original target mode, and then just a bit modify by bit modifying the mapped operators, we can define GUZI C as a linear combination of this form. Then it can be proved that the GUZI A, GUZI C is independent mode. That means that the commutation relation becomes 0. Furthermore, introduced A and C system is pure because if we evaluate the covariance of this Gaussian state, covariance matrix have this structure. This covariance matrix is represent quantum state with purity condition is satisfied. Furthermore, by looking at this covariance structure of this covariance matrix more carefully, this covariance matrix just represents the two-mode squeeze state. So by applying this procedure of purification, we obtain that purification of A is just totally pure two-mode squeeze state. This is a very well-known result. So using this result, we evaluate the behavior of entanglement in the jitter space. This plot shows that scale dependence of the squeezing parameter. Squeezing, I mean that in this model, in this case, this two-mode state parameter A has a meaning of squeezing. So as a parameter A becomes larger, the state approaches the ideal EPR state. So in this, from this behavior of squeezing parameter A in the jitter space, squeezing will become monotonically increase as proportional to the considering scale delta. So as a result, entanglement entropy increase as proportional to the scale. So then, as we identify operator form of partner, it is possible to reconstruct a spatial shape, spatial profile of partner. So we express the operator as integral of original field barrier. And so we can extract the form of window function that represent the shape of partner mode. This is the result. We consider two different coarse-graining scale. Left one is a very small coarse-graining scale, smaller than Hubble horizon scale. In this case, shape of mode localized within horizon scale, nearly localized. But when the coarse-graining scale becomes larger, window function for the partner mode delocalize and extend over the super-horizon scale. This is a very peculiar feature of partner mode in digital space for large coarse-graining scale. So applying this method to the two-mode case, we can easily obtain the partner mode for this case. I skip a detail of calculation. The setup is here. We prepare original two mode, and we want to find out the purification mode C and D. This is partner mode. So original mode is expressed by covariance matrix with this form, a so-called standard form of the Gaussian two-mode state. Then you can obtain the partner mode CD, which satisfies this commutation relation. So the original mode and the partner mode is independent, and totally four mode constitute a pure state. And covariance matrix of totally four modes has this structure, a bit complicated form, and we can show that this type of state can be generated by 6 squeezing operator to the independent for Gaussian vacuum state. Anyway, this is a result of purification. So we can explicitly obtain the partner mode for the C and D. So using this, we can study the entanglement behavior. So this panel shows the reduced two-mode entanglement of reduced two-mode. As we prepared four modes, we can trace out two-mode and can consider the behavior of reduced two-mode. So from this plot, this AB is original two-mode, and this behavior we have already known. But as a connection to the partner mode, so the entanglement between A and C behavior is non-trivial. At first, entanglement between partner mode A and partner mode increases, but after the AB becomes separable, AC entanglement between A and C start to decrease. On the other hand, we can also check the behavior of reduced three mode. For three mode, for any partition, for every partition, it can be shown that the negativity increases with corresponding scale. So from this observation, we can say something about several things about the feature of entanglement in this system. First, target mode AB is separable on superhorizon scale. And entanglement between A and C increases until AB becomes separable. So this shows some kind of trade-off relation between AB and AC holds a so-called monogamy property of entanglement. On the other hand, on superhorizon scale, reduced 3 mode has genuine tripartite entanglement. This means that this corresponds to this figure. For superhorizon scale, all two partition for every entanglement between reduced 2 mode is lost. And just only the 3 mode entanglement between the entanglement between 3 mode survives. So the this figure represents such a structure of entanglement. Anyway, this feature is resembled to the GHD state for the qubit case, which is stated represented by this form. Qualitatively has a similar structure to the GHD state. So as a final result of my analysis, we show the spatial profile of obtained partner mode C and D. This is just same for the single mode case, and window function for the partner mode extends over the superhorizon scale. So this is a very schematic picture of the situation. For small cross-covering scale case, partner mode has a very narrow window function, but for the large cross-covering scale, partner mode has very broad tail of window function. So from this observation, it may be possible to understand the entanglement structure in the jitter space. So this picture shows that entanglement of original ABCD 4 mode state. This is a pure state, and we assume some bipartition of this four mode state and evaluate negativity. So entanglement between these, for example, A, B, and CD increases with scale, and this behavior captures a large-scale entanglement, multipartite effect. So this feature may correspond to the existence of large-scale entanglement in the jitter space. So concerning the large-scale entanglement in the jitter space, we have done the numerical calculation of 1+1 harmonic chain in the jitter space, and numerically confirms that there always exists the large-scale entanglement between two spatial regions for any separation of two regions. Two spatial regions are entangled even for superhorizon scale separation. This property is confirmed by our numerical calculation. So I summarize my talk. We consider the structure of entanglement with jitter inflation, then the entanglement harvesting with two detectors and two modes. Harvesting with two mode AB is impossible superhorizon scale to spatial region becomes separable. And this is due to the local noise of the jitter space and that kills the quantum correlation. But this is related to the monogamy of entanglement. So this behavior can be understood from the monogamous property of by introducing partner modes. So we construct the four-mode purification for original mode and obtain the spatial profile of partner modes, which are unlocalized over super-Horizon scale. And using this partner mode, negativity with 2x2 bipartition and 1x2 bipartition are considered, especially 1x2 bipartition case. The state has a similar entanglement structure as GHD type. And this behavior reflects the structure of multipartite entanglement in digital space. So I finished my talk. Thank you.
Thank you very much. So now this talk is open for the questions. So if you have a questions or comment, please raise your hand. Okay, Yoshino-san, please.
Thank you very much for your very interesting talk. My question is, so does your result mean that if we study 3-point or 4-point correlation functions in the CMB, we would be able to detect the effect of entanglement, right?
So you assuming based on the Gaussian state? You mean?
Yeah, basically, yeah.
But the Gaussian state is reducible to the for Gaussian state of multiple by Wick-Sellen. So you mean the what do you mean to?
So I mean I would like to how to say ask about the observational implication. So so in short, can we detect the effect of entanglement?
So you mean that
CMB.
is it possible to detect very large scale entanglement as in the for example CMB
in the
or
CMB. Yeah.
I'm not sure, but it may, in principle, possible, but in practically very difficult because the signal is very small.
Okay.
And beyond the limit of present technology of measurement observation.
Okay. Yeah. Thank you. Thank you.
Any other questions or comment? So I have a naive comment. So I'm coming from the condensed matter physics, and so I'm not so familiar with this situation. But in the introduction, you said that how to say this research is related to the how to say assumption of the how to say that there exists the classical distribution which mimics the quantum collision. So the second topic, so for multipartite entanglement indicate what kind of the information for that assumption. So
so in introduction, I stated the assumption of practicality just by stressing the program difficulty of applying the quantum theory and to the early universe and using that result to translate for the initial condition of classical evolution. So many researchers may do not touch that very difficult problem, and so yeah. So we don't have the answer to that treatment. That treatment is correct or not.
Okay. But if your second result is reliable or huge, so it may cause that if we use the classical initial state, we cannot expect exactly simulate the true global structure in the
Yeah, yeah.
universe.
So as a Yoshino-san's question, there may be some possibilities that some signal of quantumness or entanglement will appear in the observational data, but I'm not sure.
Okay, thank you. So, any other questions? If not, let's thank the speaker again.
Thank you.
Okay, the next talk will start the 4:30. So we have about 7-minute break.
Okay, so Kobo-san, let me share my slide.
Yes, please.
Okay. Can you hear my slide and pointer?
Yes, good.
And